Hey, sleepers. Welcome to Sleepy Lectures, the show where bedtime meets the gentle hum of the digital world, and staying awake is strictly optional. Tonight, we're drifting through a universe made of thought and light, of logic and learning. Imagine a vast, quiet library at night. The air is cool and still. The only sound is the soft, rhythmic breathing of ancient books on their shelves. But in the corner, a single computer terminal glows with a gentle, pulsing light. It's not making a sound, but you can almost feel it thinking, sorting through endless corridors of information, connecting ideas like constellations in the night sky. That quiet, glowing screen is our destination tonight. It's a doorway into the world of artificial intelligence. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Your support is a quiet, welcome encouragement. And as you settle in, I'd love to know where you're listening from. Feel free to leave your city or country and your local time in the comments. It's a lovely way to feel connected, knowing we are all listening together under different skies in different moments of the night. So, close your eyes, take a deep breath, and get ready to drift off as we explore the fascinating science behind artificial intelligence and more. Let's begin not with circuits and code, but with a dream. A very old dream. It's a question that humans have whispered to themselves for centuries, perhaps by crackling fires or under a blanket of stars. Can a thing that is not alive think? Can we create a companion from metal or clay that understands us, that can reason or create, or even just play a simple game with us? This dream is woven into our oldest stories. Long before the first computer was ever imagined, the ancient Greeks told tales of Hephaestus, the god of invention and the forge. He was said to have built brilliant, golden servants. These were not just statues. They could move. They could speak. They could assist him in his fiery workshop. They were, in a way, the very first imagined robots. Then there was Talos, a giant man made of bronze, created to protect the island of Crete. He would circle the island 3 times a day, a tireless guardian. He wasn't alive in the way we are. He was a construct, an automaton. But he performed a complex task. He had a purpose. He followed a set of instructions. These stories tell us something important. They show us that the desire to create artificial life, or at least the illusion of it, is not a modern obsession. It is a deep and ancient part of our own human nature. We are tool makers. We are storytellers. And we have always been fascinated by the boundary between the things we make and ourselves. As centuries passed, this dream moved from myth into the workshops of brilliant inventors. During the Middle Ages and the Renaissance, craftsmen in Europe began building incredible automata. These were complex clockwork creations designed to mimic life. There were mechanical monks that could walk and pray. There were birds that could sing. There were figures that could write a short phrase or play a musical instrument. One of the most famous, and perhaps a little bit mischievous, was a device from the late 1700s called the Mechanical Turk. It was a magnificent wooden cabinet, and seated behind it was a life-sized model of a man dressed in Turkish robes. This automaton could play a formidable game of chess. It toured Europe and the Americas, defeating many skilled opponents, including famous figures like Napoleon Bonaparte and Benjamin Franklin. People were amazed. How could a machine of wood and gears play a game of strategy and foresight? For decades, it was a profound mystery. The secret, of course, was that it was a clever illusion. A human chess master was ingeniously hidden inside the cabinet, operating the machine. The Mechanical Turk is a wonderful story because it highlights the difference between the appearance of intelligence and the real thing. It was a trick, a brilliant one, but it wasn't thinking. It was a puppet. Yet, it sparked the imagination. It made people ask, what if it wasn't a trick? What if a machine could really play chess on its own? The first real steps toward that future came not from a chess player, but from a pair of brilliant minds in 19th century England. Their names were Charles Babbage and Ada Lovelace. Charles Babbage was a mathematician and inventor, a man brimming with ideas. He was often frustrated by the errors he found in hand-calculated mathematical tables. Humans, he realized, get tired, they get distracted, they make mistakes. A machine would not. So he designed a machine called the difference engine. Imagine a massive, intricate calculator made of brass and pewter gears. It was designed to perform one specific, but very complex, job: to calculate mathematical tables automatically and flawlessly. It was a marvel of mechanical engineering, a testament to precision. But Babbage had an even grander idea. He dreamed of a machine that wasn't limited to just one task. He called it the analytical engine. This was the true ancestor of the modern computer. Unlike the difference engine, which was like a specialized tool, the analytical engine was designed to be programmable. It could be given a set of instructions on punched cards, similar to how a jacquard loom used cards to weave complex patterns in fabric. This meant it could, in theory, solve any number of different problems. It could add, subtract, multiply, and divide. It could even make decisions based on the results of its calculations. It was a revolutionary concept, a machine that could follow a recipe, any recipe you gave it. But Babbage was a man ahead of his time. The technology of his day wasn't quite up to the task of building his magnificent room-sized engine. It remained, for the most part, a dream on paper. But someone else saw the true, profound potential in Babbage's designs. And this is where our story takes a truly remarkable turn. Her name was Ada Lovelace. She was the daughter of the famous poet, Lord Byron, but her passion was not for poetry. It was for mathematics, which she called poetical science. Ada met Charles Babbage and was captivated by his work on the analytical engine. She understood it on a level that few others did. She translated an article about the engine from French into English, but she did more than just translate. She added her own extensive notes, which ended up being 3 times longer than the original article. And in these notes, Ada Lovelace laid out a vision that was breathtakingly ahead of its time. Babbage saw his machine as a powerful number cruncher, a calculator. Ada saw something more. She realized that if the machine could manipulate numbers, and if other things, like words or music or images, could be represented by numbers, then the machine could manipulate anything. She wrote that the analytical engine might one day be used to compose elaborate pieces of music. It could be used to create art. It was not, she argued, just a machine for calculation. It was a machine for creation. It could process symbols, not just numbers. In her notes, she also wrote out what is now considered to be the world's first computer program. It was a detailed algorithm designed to be run on the analytical engine. For this reason, Ada Lovelace is celebrated today as the first computer programmer. She was a prophet of the digital age, writing about software a full century before the first electronic computers were built. She saw the poetry in the machine. She understood that it wasn't just about gears and logic, but about imagination and potential. She understood that this wasn't just about making calculations faster. It was about creating a new way to think. Let's just pause there for a moment. Imagine Ada in Victorian England, surrounded by gas lamps and horse-drawn carriages, dreaming of a machine that could compose music. It's a testament to the power of human imagination, the ability to see beyond the world as it is, and to glimpse the world as it could be. That vision, that dream of a thinking, creating machine, is the seed from which all of artificial intelligence has grown. The seeds planted by Babbage and Lovelace lay dormant for nearly a century. The world was not yet ready for their vision. It would take 2 world wars and a revolution in electronics to create the machines that could finally begin to fulfill that ancient dream. The next great leap forward comes with a name that is now synonymous with computer science and artificial intelligence: Alan Turing. Turing was a British mathematician, a brilliant, gentle, and unconventional thinker. During World War II, he played a pivotal role in breaking the German Enigma code. The Enigma machine was a device used by the German military to send encrypted messages. It was incredibly complex, with millions of possible settings. Cracking it by hand was thought to be impossible. Turing and his team at Bletchley Park developed a machine called the bomb. It was an electromechanical device that could rapidly test thousands of possible Enigma settings. It automated the logical process of code breaking. This work was top secret, but it was a profound demonstration of a machine performing a task that required a kind of intelligence. It was finding patterns. It was testing hypotheses. It was solving a puzzle far too complex for the human mind alone. After the war, Turing turned his attention back to a more fundamental question, the same question that echoed through the myths of Hephaestus and the work of Ada Lovelace. Can a machine think? Turing knew this was a difficult philosophical question. How do you even define thinking? So he proposed a clever way to reframe the problem. He devised what he called the imitation game, which we now know as the Turing test. Let's visualize it. It's a very simple setup. Imagine you are in a room and you are communicating with 2 other entities through a text-based chat. You can't see them or hear them. One of them is a human. The other is a computer program. You can ask them any questions you want. You can talk about the weather, poetry, your feelings, anything at all. Your job is to figure out which one is the human and which one is the machine. Turing argued that if a machine could carry on a conversation so effectively that a human interrogator couldn't tell it apart from a real person, then for all practical purposes, that machine could be said to be thinking. It's a subtle and powerful idea. He sidestepped the messy philosophical debate about consciousness and inner experience. He focused on behavior, on capability. If it acts intelligent, if it communicates intelligently, then we should consider it intelligent. The Turing test gave the fledgling field of computer science a concrete goal, a North Star to aim for. It was no longer just a vague dream. It was a challenge. The world was finally catching up to the dreamers. The 1940s and 50s saw the birth of the first electronic computers. Machines like ENIAC and UNIVAC. They were enormous, filling entire rooms. They were powered by thousands of fragile vacuum tubes that hummed and glowed with heat. They were programmed by physically plugging and unplugging cables, but they were fast, incredibly fast. They could perform calculations in a few minutes that would take a human mathematician a lifetime. With these new, powerful tools in hand, a group of visionary scientists felt that the moment had finally arrived. In the summer of 1956, a small group of mathematicians and researchers gathered for a workshop at Dartmouth College in New Hampshire. It was here that the name for this new, exciting field was officially coined. John McCarthy, a young mathematics professor, proposed they call their subject artificial intelligence. The name stuck. The mood at that Dartmouth workshop was one of incredible optimism. The attendees, who would become the founding fathers of AI, people like McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon, were convinced that a major breakthrough was just around the corner. They believed that every aspect of learning or any other feature of intelligence could, in principle, be so precisely described that a machine could be made to simulate it. They made a bold prediction. They thought that a team of researchers working for one summer could make significant progress in creating a truly thinking machine. Of course, it turned out to be a little more complicated than that, but their optimism was infectious. It fueled the first great wave of AI research. The approach they took is now often called symbolic AI, or sometimes affectionately, good old-fashioned I. The core idea was that human thought is based on manipulating symbols. When we think, we are essentially following a set of logical rules. Think about it like grammar. To form a sentence, you follow rules. A noun, a verb, an object. The cat sat on the mat. It's a structure. The GOFI pioneers believed that all knowledge could be broken down into such rules and facts. Let's use a simple analogy. Imagine you wanted to build an AI that could be a detective. Using the symbolic approach, you would try to write down every single rule a detective knows. Rule number 1. If the fingerprints at the crime scene match a person in the database, that person is a suspect. Rule number 2. If a suspect has a weak alibi, their likelihood of being guilty increases. Rule number 3. If a witness saw a person fleeing the scene, get a description of that person, and so on. You would try to create a massive, intricate rulebook for detective work. The AI would be an expert system. It wouldn't learn in the way we do. It would be given all the knowledge up front as a giant library of if-then statements. This approach led to some impressive early successes. A program called the Logic Theorist, created by Newell and Simon, was able to prove several mathematical theorems. It was a stunning achievement. A machine was performing abstract reasoning. Another program could solve complex algebra word problems. And of course, they started working on chess, a game of pure logic and rules, perfect for symbolic AI. These early programs created a buzz of excitement. It seemed like the dream of the Dartmouth workshop was on the verge of coming true. The machines were reasoning. They were solving problems. The age of thinking machines had truly begun. But as the 1960s rolled on, researchers started to hit a wall. A very big, very human wall. The problem was something we all have, but we rarely think about. It's called common sense. Think back to our detective AI. You can give it millions of rules about fingerprints and alibis. But what about a rule like this? People don't usually confess to a crime they didn't commit just for fun. Or, a suspect who is a fish probably didn't steal the diamonds. These things are completely obvious to us. We don't need a rule for them. We just know them. This vast, unspoken web of knowledge about how the world works is common sense. How do you program that? How do you write down every single mundane fact about the world? a cup is smaller than a table. You can't fold a bowling ball. If you let go of a pen, it will fall down, not up. The sheer amount of information is staggering. Researchers tried to build huge knowledge bases, but the task was monumental. It was like trying to empty the ocean with a teaspoon. This led to some funny and frustrating failures. An early machine translation program trying to translate the English phrase, "The spirit is willing, but the flesh is weak," into Russian, and then back into English, famously returned the phrase, "The vodka is good, but the meat is rotten." The AI had the dictionary definitions. It had the grammar rules. But it had no understanding of context, no common sense. Another major challenge was that symbolic AI systems were very brittle. They worked perfectly within their narrow, predefined set of rules. But if they encountered a situation they hadn't been explicitly programmed for, they would simply break. They couldn't adapt. They couldn't generalize. This growing realization that the problem was far harder than anyone had anticipated led to a period of disillusionment. The grand promises of the early years had not been met. Government agencies, like DARPA in the United States, which had been a major source of funding, started to cut back. In the United Kingdom, a highly critical report called the Lighthill Report essentially declared that AI research had failed to live up to its hype. Funding dried up. Research labs scaled down. The buzz of excitement was replaced by a quiet sense of disappointment. This period, from the mid-1970s to the early 1980s, became known as the first AI winter. It was a time of quiet reflection for the field. The dream wasn't dead, but it was clear that the path forward was not as simple as writing down an endless list of rules. A new approach was needed, a new inspiration, and that new inspiration would come not from logic and symbols, but from looking inward, from looking at the 3-pound universe inside our own skulls, the human brain. While a world of symbolic was having its moment in the sun and then entering its winter, another, quieter idea had been developing in the background. It was an idea inspired not by logic books and grammar, but by biology. It asked a different question. Instead of trying to program intelligence rule by rule, what if we could build a machine that learns intelligence on its own, the way a child does? This approach is based on the structure of the brain itself. The brain is not a giant rule book. It's a network, a vast interconnected web of tiny cells called neurons. There are billions of them. Each neuron is a very simple little processor. It receives signals from other neurons. If the combined signals are strong enough, it fires, sending its own signal out to other neurons connected to it. That's it. That's the basic mechanism. A simple process of receiving signals and firing. But out of this simple process, multiplied billions of times over, emerges everything we are. Our thoughts, our memories, our ability to see a face in a crowd, or to feel the warmth of the sun. Intelligence, from this perspective, is not a set of rules. It is an emergent property of a complex, interconnected network. As early as 1943, 2 researchers, Warren McCulloch and Walter Pitts, proposed a simplified mathematical model of a biological neuron. Their artificial neuron was a very basic little thing. It could take a few inputs, which were just numbers, and produce a single output, usually a 1 or a 0, on or off, fire or don't fire. This was a tiny, humble beginning, but it was the seed of a powerful idea. What if you could connect many of these artificial neurons together, just like in the brain? Could this artificial neural network learn to do interesting things? In 1958, a psychologist named Frank Rosenblatt took this idea and built a machine called the perceptron. The perceptron was one of the first physical implementations of a neural network. It was designed for a simple task: image recognition. It had a grid of 400 photocells, like a primitive digital eye. These photocells were connected to a network of artificial neurons. Rosenblatt would show the perceptron a card with a shape on it, say a triangle. The machine would make a guess. If it was wrong, the operator would give it a little nudge. This nudge would slightly adjust the strength of the connections between the neurons. If a connection led to a correct guess, it was made a little bit stronger. If it led to a wrong guess, it was made a little bit weaker. Let's try a visualization moment here. Imagine a beautiful, sprawling garden. The garden is filled with hundreds of tiny, magical springs. These are your inputs. They can be either on or off, flowing with water or dry. At the other end of the garden is a single large fountain. This is your output. Your goal is to get the fountain to turn on only when a specific pattern of springs is active. Between the springs and the fountain is a complex network of tiny channels carved into the earth. These are the connections, the pathways. When you first start, the channels are all the same depth. Water flows through them, but not very efficiently. Now, you start to train your garden. You turn on the pattern of springs that you want to recognize. Water flows through the channels. Some of that water reaches the fountain, but maybe not enough to turn it on. So you walk through the garden with a small trowel. You find the channels that the water flowed through, and you dig them just a little bit deeper. You make them stronger. Then you show the garden a different pattern, one you don't want it to recognize. Water flows through a different set of channels. You walk through the garden again, but this time, you fill in those channels a little bit. You make them weaker. You repeat this process over and over. Show it a good pattern, deepen the active channels. Show it a bad pattern, fill in the active channels. Slowly, patiently, the garden learns. The correct pathways become deep and wide, like well-worn riverbeds. The incorrect pathways become faint and shallow. Eventually, the network of channels becomes so perfectly sculpted that when you activate the correct pattern of springs, a powerful surge of water flows directly to the fountain, and it roars to life. But when you activate any other pattern, the water just trickles away, and the fountain remains still. The garden wasn't programmed with rules. It learned. It shaped itself in response to experience. This is exactly what Rosenblatt's perceptron did, with electrical signals instead of water. And it worked. It could learn to distinguish between different letters of the alphabet or simple shapes. It was an exciting proof of concept. The New York Times ran an article in 1958 declaring that the perceptron was the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The optimism was back, but once again, it was a bit premature. In 1969, two of the pioneers from the Dartmouth workshop, Marvin Minsky and Seymour Papert, published a book called Perceptrons. In it, they proved mathematically that a simple single-layer perceptron like Rosenblatt's had severe limitations. It could only learn to solve problems that were linearly separable. That sounds technical, but the idea is simple. Imagine you have a piece of paper with red dots and blue dots scattered on it. If you can draw a single straight line to separate all the red dots from all the blue dots, that problem is linearly separable. A perceptron could learn to do that. But what if the red dots are in a circle in the middle, and the blue dots are all around them? You can't separate them with a single straight line. A simple perceptron couldn't solve that puzzle. This book had a chilling effect on neural network research. Many in the AI community concluded that it was a dead end. Combined with the other challenges of the AI winter research into neural networks slowed to a crawl for more than a decade. The idea, it seemed, was too simple to solve the complex problems of the real world. But a small, dedicated group of researchers never gave up on the idea. They believed that the problem wasn't the concept of the neural network itself, but the simplicity of the early models. What if the answer wasn't a single layer of neurons, but many layers stacked one on top of the other? What if you created a deep neural network? This is the core idea behind what we now call deep learning. Let's go back to our garden analogy. The single-layer perceptron was like having just one set of channels between the springs and the fountain. It was limited in the complexity of the patterns it could learn. But a deep neural network is like having multiple gardens, one after the other. The springs in the first garden are the initial input, say, the pixels of an image. The fountains of that first garden don't lead to a final output. Instead, they feed into the springs of a second garden, and the fountains of the second garden feed into the springs of a third garden, and so on. Only the fountains in the very last garden represent the final answer. This layered structure allows the network to learn in a much more sophisticated way. It creates a hierarchy of knowledge. Let's imagine we're trying to build a deep learning model that can recognize a picture of a cat. The first layer of neurons, the first garden, might learn to recognize very simple things. It's like a team of tiny specialists. One neuron might learn to fire only when it sees a vertical edge. Another fires when it sees a horizontal edge. Another looks for a small patch of a certain color. Their job is very, very basic. Now, they pass the results to the second layer. This second layer doesn't see the original image pixels. It sees the output of the first layer. It sees a world made of edges and colors. So, its neurons can learn to combine these simple features into slightly more complex shapes. One neuron in this layer might learn to fire when it sees a combination of a curved edge and a pointed edge, something that looks a bit like an ear. Another might learn to recognize a combination of two small, dark circles, which could be eyes. Another might learn to recognize the texture of fur. Then, this second layer passes its findings to a third layer. This third layer now sees a world of ears, eyes, and fur textures. So, its neurons can learn to combine those features. One neuron might learn that the combination of two pointy ears, a pair of eyes, and a small nose, all arranged in a particular way, is a cat face. Another might learn to recognize the shape of a cat's body or a tail. Finally, the output from this layer goes to the final layer, which makes the decision. If the cat face neuron and the cat body neuron are both firing strongly, the final output neuron will fire and say, "Yes, this is a picture of a cat." Do you see the beauty of this? No one ever told the network to look for ears or eyes or fur. It discovered these concepts on its own, layer by layer, just by being shown thousands and thousands of pictures of cats and being told, "This is a cat," or "This is not a cat." It built up its own understanding of what a cat is, from the simplest pixels to the most abstract idea of catness. This hierarchical learning is what makes deep learning so incredibly powerful. It can find subtle patterns in data that a human programmer would never even think to look for. For many years, this idea of deep learning was mostly theoretical. Training these deep networks was computationally very, very expensive. It required a huge amount of processing power that simply wasn't available. And there was another problem: data. To train a deep neural network to recognize cats, you need a lot of pictures of cats. Thousands, millions even. And you need them to be labeled. Someone has to go through and tag each picture: cat, dog, car, tree. In the early days, such a massive labeled dataset simply didn't exist. The tide began to turn in the 2000s and early 2010s, thanks to three key breakthroughs that happened at around the same time. First, the rise of the internet and digital cameras meant that for the first time, massive amounts of data were becoming available. Second, computer processors became much, much faster. In particular, researchers realized that graphics processing units, or GPUs, the chips designed to render the complex graphics in video games, were perfectly suited for the kind of mathematics required to train neural networks. Suddenly, the computational power was there. And third, and this is a crucial part of the story, was the creation of a project called ImagineNet. A computer scientist at Stanford University named Dr. Fei-Fei Li recognized that the lack of a large, high-quality dataset was a major bottleneck for the entire field of computer vision. So she and her team embarked on an ambitious project to create one. They gathered millions of images from the internet and used a crowdsourcing platform to have people all over the world label them. What is in this picture? A mushroom, a motor scooter, a leopard. ImagineNet was the food that the hungry deep learning models had been waiting for. It was a vast, rich, and challenging dataset that researchers could use to test and train their creations. In 2012, a team led by Geoffrey Hinton, one of the steadfast researchers who had kept the faith in neural networks through the AI winter, entered a model called AlexNet into the annual ImagineNet competition. Their deep neural network didn't just win. It shattered all previous records. It was a watershed moment. The world of eye research was stunned. Suddenly, deep learning was no longer a niche, theoretical idea. It was the future. The A winter was definitively over, and a new spring had arrived, powered by deep neural networks, big data, and powerful computers. The quiet, patient work of Hinton, along with other pioneers like Jan LeCun and Yoshua Bengio, who are often called the godfathers of deep learning, had finally paid off. They had shown the world that by imitating the brain structure, we could create machines that could learn to see, understand, and interact with the world in ways that were previously the stuff of science fiction. The age of modern AI had truly begun. So, now that we have this powerful tool, the deep neural network, it's helpful to take a small step back and look at the different ways we talk about artificial intelligence. The term gets used a lot, and it can mean many different things. So let's gently unpack it, like opening a series of nested boxes, each one revealing a more specific idea. The first and broadest way to categorize A is by its capability. We usually talk about 3 levels here. The first level is called Artificial Narrow Intelligence, or ANI. This is the only kind of eye that we have successfully built so far. It's also sometimes called weak eye, but that name is a bit misleading because this type of AI can be incredibly powerful. The key word here is narrow. An AI is an AI that is specialized for one specific task. It is an expert in its own small domain, but it has no understanding or consciousness outside of that domain. Think of the AI that plays chess. It can be the best chess player in the world, capable of defeating any human grandmaster. But that's all it can do. You can't ask it for a weather forecast. You can't have a conversation with it about its favorite color. It doesn't know what a color is. It doesn't know anything in the human sense. It just knows the rules and strategies of chess. We are surrounded by narrow AI every single day. It's the gentle, invisible hum in the background of our digital lives. When you open a music streaming app and it suggests a new song you might like, that's a recommendation engine, a form of Annie. It has analyzed your listening history and the habits of millions of other users to find patterns and make a good guess. When you get an email and it's automatically sorted into your spam folder, that's an Annie at work. It has learned to recognize the patterns of junk mail. The navigation app on your phone, it finds the fastest route to your destination. Weaving through real-time traffic data is a sophisticated Annie. Even the simple act of searching for something online uses powerful Annie to sift through billions of web pages and give you the most relevant results in a fraction of a second. All of these are incredibly useful tools. They are intelligent in their own narrow way, but they are not self-aware. They are not conscious. They are simply very complex patterns of math and logic designed to solve a specific problem. The next level up is the one that has captivated science fiction writers and philosophers for decades. This is artificial general intelligence, or AGI. This is sometimes called strong AI. An AGI would be a machine that possesses the ability to understand, learn, and apply its intelligence to solve any problem, much like a human being. It wouldn't be limited to one task. It could learn to play chess, and then learn to write a poem, and then learn to cook a meal, and then have a meaningful conversation about the experience. It would have common sense. It would be able to transfer knowledge from one domain to another. This is the kind of AI you see in movies. The helpful android companion, the curious robot explorer. It is the dream that drove the early pioneers at the Dartmouth workshop. It's very important to be clear about this. AGI does not currently exist. It is a theoretical goal, a subject of ongoing research and debate. Building an AGI is an extraordinarily difficult challenge. We don't even fully understand how our own general intelligence works. How does consciousness arise from the firings of our neurons? We don't know. And until we do, creating it artificially remains a distant and profound challenge. The third and final level is even more theoretical. It's called artificial superintelligence, or ASI. An ASI would be an intellect that is much smarter than the best human brains in practically every field, including scientific creativity, general wisdom, and social skills. This is a concept that invites a lot of deep philosophical thought. It's not something to be anxious about, but something to contemplate with a sense of wonder and humility. It forces us to ask big questions about the nature of intelligence itself and our place in the universe. For now, it remains firmly in the realm of speculation, a distant star in the intellectual sky. So those are the three main capability levels: narrow, general, and super. Right now, we live in a world of narrow A. Now let's open the next box. Within the world of AI, there are several important subfields. These are the different approaches and disciplines that researchers use to build these systems. The most important one, which we've already discussed, is machine learning, or ML. This is the engine that drives most modern AI. It is the heart of the revolution. Machine learning is a subfield of AI that focuses on building systems that can learn from data, identify patterns, and make decisions with minimal human intervention. Instead of programming an AI with explicit rules, you give a machine learning model a large dataset and an algorithm that allows it to learn the rules for itself. The deep neural network we explored is a powerful type of machine learning model. The process of showing the network cat pictures and letting it adjust its connections is the learning part of machine learning. Within machine learning itself, there are different styles of learning. The cat example we used is called supervised learning. It's supervised because a human has provided the labels. We told the machine, this is a cat, this is not a cat. We gave it the correct answers to learn from. This is great for tasks like classification and prediction. There's also unsupervised learning. In this case, you give the machine a lot of data, but you don't give it any labels. You just say, here is a pile of information. Find some interesting patterns or structures in it. The AI might help at a customer database and discover, on its own, that customers tend to fall into 3 distinct groups based on their purchasing habits. It doesn't know what to call these groups, but it has found the clusters. This is useful for things like market segmentation or finding anomalies. And there's a third, very interesting style called reinforcement learning. This is learning through trial and error, guided by rewards and punishments. Let's use another gentle analogy. Imagine you are teaching a small, simple robot to navigate a maze. The robot doesn't have a map. It has to learn on its own. Every time it takes a step, you give it feedback. If it moves 1 step closer to the exit, you give it a small reward, a little point. If it bumps into a wall, you give it a small penalty. You take away a point. If it reaches the exit, you give it a big reward. The robot's goal is to maximize its total reward. At first, it just wanders around randomly. But over time, it starts to learn. It realizes, oh, when I turn right at this corner, I usually get a reward, but when I turn left, I usually hit a wall and get a penalty. So it becomes more likely to turn right in the future. After many, many trials, it learns an optimal path through the maze, a strategy that gets it the most points. This is reinforcement learning. It's very powerful for teaching an AI to make decisions in a complex environment. It's the technique that was used to train AlphaGo, the AI from DeepMind that famously defeated the world's best Go players. The AI played millions of games against itself, constantly tweaking its strategy through trial and error, guided by the simple reward of winning or losing the game. So, we have machine learning as the broad engine. Now for a few other important subfields. One is natural language processing, or NLP. This is the branch of AI that deals with helping computers understand, interpret, and generate human language. Language is incredibly complex. It's full of ambiguity, sarcasm, context, and cultural references. Teaching a machine to handle it is a huge challenge. When you speak to a voice assistant on your phone or smart speaker, NLP is what translates your spoken words into text, figures out what you mean, and generates a spoken response. When you use an online translation service, that's NLP at work. Chatbots, grammar checkers, and systems that can summarize long articles are all applications of NLP. They are learning the patterns of our language, just like a neural network learns the patterns of an image. Another major subfield is computer vision. This is the area of AI dedicated to enabling machines to see and interpret the visual world. Just like NLP deals with language, computer vision deals with images and videos. Our cat recognition example was a classic computer vision task. Other applications include facial recognition systems, medical imaging analysis, where an eye can help a radiologist spot tumors in an X-ray, and the systems in self-driving cars that identify pedestrians, traffic lights, and other vehicles. It's about teaching a machine to make sense of the stream of pixels coming from a camera, to see the world not just as data, but as objects, scenes, and events. So, as we close this nested box of definitions, we can see a clearer picture. Artificial intelligence is the grand, overarching field. Machine learning is the primary method used today to achieve it, and specialized areas like NLP and computer vision apply these machine learning techniques to specific types of problems, like language or images. It's not a single monolithic thing called AI. It's a rich and diverse ecosystem of ideas and techniques, all working toward that ancient dream of creating a machine that can perceive, learn, and reason. And this ecosystem is quietly and gently humming all around us in the tools and services we use every single day. Let's take a slow, gentle walk through a typical day and notice the quiet presence of this technology. It's not in the grand, futuristic ways we might imagine. It's in the small, helpful moments. It's a subtle current flowing beneath the surface of modern life. The day might begin with your phone. Perhaps you use an alarm that has an option for a smart wake-up. It monitors your sleep cycles, using the phone's microphone or motion sensors, and tries to wake you during a period of light sleep so you feel more refreshed. That small decision, when to sound the alarm, is guided by a simple AI model. You reach for your phone and scroll through a news feed or a social media app. The content you see is not random. It's not even purely chronological. It has been curated for you by a powerful recommendation algorithm. This is a form of narrow A. It has learned from your past behavior, what you've liked, what you've shared, what you've paused to read, and it's making a prediction about what you will find interesting right now. It's trying to build a personalized newspaper just for you. You check the weather forecast. The prediction for rain later today isn't just based on a single satellite image. It's the product of incredibly complex AI models that analyze vast amounts of data from weather stations, satellites, and atmospheric sensors all over the world. They are running simulations of the atmosphere, looking for patterns that predict how weather systems will move and evolve. Now it's time for breakfast. You might decide to listen to some music. You open your favorite streaming service and hit play on a personalized playlist. Discover Weekly or your daily mix. This playlist feels like it was made by a friend who knows your taste perfectly. In a way, it was. It was made by an eye that has analyzed the musical DNA of millions of songs, their tempo, their key, their instrumentation, and has compared your listening history to that of millions of other people. It has found a tribe of listeners who like the same weird indie band you do, and it's showing you what else they listen to. It's a quiet act of connection, facilitated by math. Let's imagine you need to travel somewhere. You get in your car or open a ride-sharing app. You type in your destination. The map that appears with its calm blue lines showing the best route, is a product of AI. It's not just calculating the shortest distance. It's analyzing real-time traffic data, fed by the anonymous location data from thousands of other phones. It sees a traffic jam forming on the highway and silently reroutes you through quiet side streets. It's solving a massive dynamic puzzle in real time to save you a few minutes of your day. If you're driving a newer car, AI is working in other, more subtle ways. Your car might have an advanced driver assistance system. Features like lane keeping assist, which gently nudges the steering wheel if you start to drift, or adaptive cruise control, which automatically maintains a safe distance from the car in front of you. These systems use cameras and sensors, processed by computer vision algorithms, to perceive the world around the car and make small, helpful adjustments. Once you arrive at work or sit down to study, the gentle hum continues. You open your email inbox. It's clean and mostly free of junk. That's because a sophisticated AI spam filter has already read through hundreds of incoming messages and quarantined the ones trying to sell you dubious miracle cures or claiming you've won a foreign lottery. It does this by recognizing patterns in the text, the sender's address, and other features that are common in spam. You start to write a document or an email. As you type, a red or blue line appears under a word. It's a spelling or grammar checker. The simple ones are just based on a dictionary. But the more advanced ones, which can suggest stylistic improvements or rephrase a clumsy sentence, are powered by natural language processing. They have been trained on vast libraries of well-written text, and they have learned the subtle patterns of good prose. They are like a quiet, helpful editor sitting on your shoulder. Need to find some information? You go to a search engine. You type in a few keywords. In less than a second, you get a list of millions of results, ranked in order of relevance. This ranking is one of the great triumphs of modern AI. The search engine's algorithms are considering hundreds of factors: the words on the page, the authority of the website, how many other sites link to it, your location, your past search history, to make its best guess about what you are truly looking for. It's a conversation with the entire world's library, and I is the incredibly fast and knowledgeable librarian. Let's move into the evening. Time to relax. You decide to watch a movie. You open a streaming service. The home screen is a mosaic of possibilities, but it's not the same for everyone. The rows of content, thrillers with a strong female lead, witty sitcoms, visually striking foreign films have been generated just for you. The artwork for the same movie might even be different for you than for your friend, based on whether the eye thinks you'll respond more to a picture of the romantic leads or a picture of the action sequence. You choose a show. You might notice a small button that says Skip Intro. How does it know exactly where the intro sequence begins and ends? Often, an eye has analyzed the audio and video of thousands of episodes, found the recurring musical theme and title sequence, and marked it for you. A small, simple convenience, born of complex pattern recognition. If you're a fan of video games, you've been interacting with an eye for years. Every non-player character, or NPC, the townspeople who wander through a village, the enemies who patrol a castle, is controlled by a form of their behaviors. From simple pathfinding to complex combat tactics, are governed by algorithms that allow them to react to your presence and actions, creating a more immersive and believable world. Even our health and wellness are being touched by this gentle current. Many people wear smartwatches or fitness trackers. These devices use sensors to monitor your heart rate, your activity levels, and even the quality of your sleep. The data is then processed by machine learning algorithms to give you insights. You were in a deep sleep for 2 hours last night. Your average resting heart rate is going down. These are not just raw numbers. They are interpretations, patterns found in the data stream of your own body. In hospitals, AI is becoming a powerful assistant for doctors. Computer vision systems are being trained to look at medical scans, X-rays, MRIs, CT scans. They can learn to spot the subtle signs of disease, like a tiny tumor or the early stages of a retinal problem. They don't replace the human doctor. They act as a second pair of eyes, drawing the doctor's attention to areas that need a closer look. They can tirelessly scan thousands of images, catching things a tired human eye might miss. And what about creativity? The domain we thought was purely human? Even here, AI is becoming a collaborator, not a replacement, but a tool. Musicians can use AI to generate new melodies or harmonies to inspire them. Graphic designers can use AI to suggest color palettes or generate different layout options. Writers can use AI tools to brainstorm ideas or overcome writer's block. This is not a new idea. As far back as the 1970s, an artist and computer scientist named Harold Cohen created a program called Aaron. Aaron, that could autonomously create original drawings. Cohen spent decades working on it, teaching it rules about composition and color. The art was a partnership between the human and the machine. As we look across the landscape of our day, from waking up to falling asleep, we can see that AI is not a single looming presence. It is 1,000 small helpful things. It is the quiet efficiency of the spam filter. It is the uncanny insight of the music recommendation. It is the life-saving potential of the medical scan analysis. It is a tool, or rather, a whole new toolbox. And like any tool, its purpose is to extend our own capabilities, to automate the tedious, and to help us find patterns and meaning in a complex world. It is the gentle hum of progress, flowing quietly all around us. As we become more comfortable with the presence of artificial intelligence in our daily lives, it's natural and healthy to also think a little more deeply about it. This isn't a source of anxiety, but a gentle invitation to be thoughtful. Just as we tend to a garden, we should also tend to the technologies we create, ensuring they grow in a way that is helpful, fair, and beautiful. One of the most important things to consider is the idea of bias. An AI model is not born with its own opinions or prejudices. It learns from the data we give it. It is a mirror reflecting the world it has been shown. Let's go back to our cat-recognizing neural network. If we train it on a dataset that contains 10 million pictures of cats, but every single one of those cats is a ginger tabby, the network will become an expert at recognizing ginger tabbies. But if we then show it a picture of a sleek, black Siamese cat, it might get confused. It might say, "I'm not sure what that is. It doesn't look like the cats I know." The AI isn't being difficult. It's just reflecting the bias in its training data. It has a skewed view of the world because we gave it a skewed education. This becomes much more important when AI is used to make decisions that affect people's lives. Imagine an AI system designed to help a company screen job applications. If, in the past, the company has mostly hired people from a certain background, and we train the AI on that historical data, the AI will learn that pattern. It might learn to favor candidates who fit the old mold and screen out qualified candidates who are different. It wouldn't be doing this out of malice. It would just be perpetuating the biases that were present in the data it learned from. This is a profound and important challenge. It reminds us that building fair and ethical AI is not just a technical problem. It's a human problem. It requires us to look carefully at our data, to be aware of our own societal biases, and to consciously work to correct them. This is why the work of computer scientists like Joy Buolamwini is so vital. She was a researcher at MIT when she discovered that some facial analysis software had much higher error rates for women and for people with darker skin tones. Why? Because the datasets used to train these systems were overwhelmingly composed of images of white men. Her work, and the work of many others, has highlighted the critical need for diversity, not just in the data we use, but also in the teams of people who build these technologies. When people from a wide range of backgrounds and experiences work together, they are much more likely to spot these kinds of biases and design systems that work well for everyone. It's about being a careful, thoughtful gardener. It's about making sure the soil of our data is rich and varied, so that the intelligence that grows from it is healthy and balanced. Another gentle puzzle to contemplate is sometimes called the black box problem. With a simple, old-fashioned symbolic AI, you could always trace its reasoning. It was following a set of rules. If it made a strange decision, you could look at the rulebook and see exactly why. With a deep neural network, it can be more complicated. A network with millions of connections, all with their own finely tuned weights, can make incredibly accurate predictions. But if you ask it why it made that prediction, it can be very difficult to get a straight answer. The reasoning is distributed across the entire network. It's in the subtle interplay of all those connections it learned on its own. Researchers are working hard on this problem, developing techniques for explainable AI or XAI. They are trying to build tools that can peer inside the black box and translate the network's mathematical reasoning into something a human can understand. For example, in a medical imaging system, an AI tool might be able to highlight the specific pixels in a scan that led the network to believe a tumor was present. This builds trust and allows the human expert, the doctor, to verify the AI's conclusion. Finally, exploring AI gently leads us to some of the most beautiful and profound philosophical questions. It holds up a new kind of mirror to ourselves. When we try to teach a machine to understand language, it forces us to confront the incredible complexity and nuance of our own communication. What is sarcasm? What is a metaphor? How do we convey so much meaning with just a few words? When we watch an AI generate a piece of art or music, it makes us. What is creativity? Is it the spark of a unique, conscious mind? Or is it the brilliant remixing and recombination of patterns learned from past examples? Or perhaps it's a little of both. AI art diminish human creativity. It invites us to appreciate it on a deeper level. And of course, there is the biggest question of all. What is consciousness? What is this subjective first-person experience of being alive? We don't have the answer. AI research doesn't provide the answer, but it sharpens the question. It gives us a fascinating point of comparison. A deep learning model can process information, find patterns, and achieve goals. But does it feel anything? Does it have an inner world? Most researchers would say no. It's just very complex math. But by building these systems that can mimic the functions of intelligence, we gain a new appreciation for the miracle that is happening inside our own minds right now. The fact that you are not just processing the sounds of my words, but you are experiencing them. You are feeling the gentle pace, the calm tone. You are connecting these ideas to your own thoughts and memories. That is the magic. The journey into artificial intelligence is not a journey into a cold, alien world of machines. It is a journey back to ourselves. It's a new chapter in the very old human story of trying to understand our own minds and our place in the cosmos. It's a path filled with wonder, with responsibility, and with an endless invitation to be curious. And so, as we begin to drift toward the end of our journey tonight, let's take one last, quiet moment to reflect. We have traveled from ancient myths of bronze giants to the glowing, whirring heart of the modern computer. We have met visionaries like Ada Lovelace, who saw poetry and logic, and Alan Turing, who dared to ask if a machine could think. We have watched ideas blossom, fade in the cold of an winter, and then re-emerge, stronger and more vibrant than before. We've come to see that artificial intelligence is not magic. It is not a mysterious sentient force that has appeared out of nowhere. It is the result of decades of patient work, of brilliant ideas, and of human curiosity. At its core, it is math. It is logic. It is, above all, the science of patterns. Let's have one final visualization moment together. Imagine you are standing on the shore of a vast, calm ocean at night. The water is perfectly still, and it stretches out to the horizon, meeting the deep, star-filled sky. This ocean represents all the data in the universe. Every word ever written, every note of music ever composed, the intricate dance of weather systems, the genetic code in a single cell, the light from a distant galaxy. It's an endless, shimmering sea of information. For most of human history, we could only experience this ocean by dipping our hands in at the shore. We could read one book at a time. We could listen to one song. We could observe the clouds above our own town. Now, imagine we have woven a new kind of net. This net is made not of rope, but of logic and mathematics. It is the net of artificial intelligence. It's a fine, intricate net, woven with the threads of neural networks and learning algorithms. We can now cast this net out into the vast ocean of data. We can gently pull it back in. And when we do, we find that it has captured things we could never have seen on our own. It has captured the subtle, hidden patterns that connect millions of songs. It has captured the faint, almost invisible signs of a coming storm. It has captured the delicate, complex relationships between proteins that might lead to a new medicine. This net doesn't understand the ocean. It doesn't feel the water or see the stars. But it is a tool that allows us to see the ocean in a new light. It reveals the hidden poetry, the underlying structure, the beautiful and intricate patterns that make up our world. The story of I is not the story of a machine becoming human. It is the story of humans becoming more capable, more insightful, more able to understand the immense and wonderful complexity of the universe around us and within us. It's a journey of discovery that is still in its very early stages. There is so much more to learn, so many more patterns to find. It's a story that we are all a part of. Every time we use our phone to find our way home, or discover a new piece of music that touches our soul, it is a reminder that our own intelligence, our own consciousness, is a remarkable and precious gift, and the tools we build are, at their best, a reflection of our own innate desire to learn, to grow, and to understand. And now, it is time to let the patterns of your own mind drift. to let the thoughts of the day gently untangle, to let the rhythm of your breathing become the only pattern that matters. It's time to let the quiet ocean of your own consciousness become calm and still, ready for the gentle currents of sleep. Good night. you.